The Arizona Department of Health Services presents Instrument Calibration Training. In this DVD, the Arizona Department of Health Services, or ADHS, will try to assist the regulated laboratory community by providing information about calibration to help laboratories meet the requirements of the new Arizona regulations promulgated on December 5, 2006. Section 1 of this DVD will discuss calibration in general, the requirements of the Arizona regulations, and more specific information about the most common calibration models used in environmental laboratories. Section 2 of the DVD will discuss conditions that may compromise calibration of an instrument. This DVD should not be considered an end-all document for training for calibration for any individual laboratory, since other calibration models may be used by a laboratory and specific conditions within a lab, such as instrument type and environment, would probably require additional training for the analyst. ADHS in this DVD has attempted to pull together much of the information that it had available about calibration so that this would not be a presentation of ADHS's own opinion of calibration, but the opinions of the wider scientific community. ADHS believes that the information being presented is accurate, having had the document reviewed by various internal and external sources. However, due to the complexity of the subject and the numerous equations, errors may be found. ADHS believes that this is a living document and that other sources may be found to change or add to this presentation at a later date. In Part 1 of the Instrument Calibration Training DVD, we will discuss the different yet common calibration models used in environmental laboratories. First, we will discuss the general models of external and internal standard calibration. Then we will proceed to cover only the following models most commonly used in environmental laboratories: power and exponential calibration, point-to-point calibration. Then several linear calibration models will be discussed, such as response calibration factor, linear calibration using a least square regression, linear force through zero, method of standard additions, and finally, weighted least square regression. The last model covered will be quadratic nonlinear calibration. We define the term calibration as reference standards with known values for selected points covering the chosen concentration range that are measured with the instrument. A functional relationship is then established between the values of the standards and the corresponding measurements. The 2003 NELAC standards definition of calibration also provides us with the concept that a relationship is indicated by the values of the represented standards and the corresponding values realized by the standards. The purpose of the instrument calibration, according to the National Institute of Standards and Technology, or NIST, is intended to eliminate or reduce bias in an instrument's readings over a range of all continuous values. Important measurement concepts related to the calibration are precision, bias, and accuracy. Precision is a measure of the degree of agreement among replicate analysis of a sample, usually expressed as a standard deviation. And bias is consistent deviation of measured values from the true value caused by systematic errors in a procedure. Last, accuracy is the combination of bias and precision of an analytical procedure, which reflects the closeness of a measured value to a true value. There are many types of calibration curve fits that are available for the analyst to use. Some of the curve fits include linear, log, power, exponent, quadratic, point-to-point, and other less commonly used curve types. An important consideration in selecting a type of calibration is the treatment of the origin. There are three ways to treat the origin: ignore, include, or force. A single level or one-point curve calibration is always calculated with linear force through zero. There are some general guidelines as to the acceptable number of reference standards that are needed to perform a calibration. The first reference to use in determining the acceptable number of calibration standards is the specific method being used. However, if there is no specific criteria listed, then standard method states to perform initial calibration with a minimum of 3 concentrations of standards for linear curve, a minimum of 5 concentrations for nonlinear curves, or as specified by the method of choice. As we discuss some of the general guidelines, it is important to remember that the reporting limit is included in the calibration range, and if the reporting limit is not included, then a reporting limit verification standard should be analyzed. According to the EPA Drinking Water Manual, if there are no calibration requirements in the method, the following are guidelines to be used. At the beginning of each day that samples are to be analyzed, a calibration curve covering the sample concentration range and all target analytes should be generated according to the approved SOP. Depending on concentration ranges, the curve should be composed of 3 or more points. In addition, the EPA Drinking Water Manual goes on to state that some calibrations are so time-consuming that an initial calibration is impractical on a daily basis. Once an initial calibration is developed and where the determinative time is extensive, such as methods 508, 508.1, 515.1, 524.2, 525.2, etc., and the instrument is very stable, the laboratory may choose to perform a daily verification standard. A daily verification standard is performed on each day that analysis is done, and the initial curve should be verified by analysis of at least one standard for each of the target analytes at the expected concentration range. This verification should be done at both the beginning and end of the analyses. Once an initial calibration has been created, we must determine what makes an acceptable calibration. An acceptable calibration assures that an instrument will produce results which meet or exceed some defined criteria with a specified degree of confidence. In order to determine the acceptable calibration, we look at the working curve that is a plot of the instrument response as a function of analyte concentration. The concentration of an unknown sample is determined by correlating its response to the mathematical relationship of concentration to the instrument response established by the curve. We first look at response factors and calibration factors. Both calibration factors and response factors are measures of the slope of the calibration relationship. Each calibration or response factor represents the slope of the line between the response for a given standard and the origin. Under ideal conditions, the factors will not vary with the concentration of the standard. In practice, some variation is to be expected. If response factors or calibration factors are used, the calculated percent RSD for each analyte of interest must be less than the method specified value, typically 20%. Refer to the applicable method for the calibration procedure and acceptance criteria on the response factors or calibration factors for each analyte. The correlation coefficient is used in analysis to show how well the independent variable and the dependent variable move together. Results can be found in both positive and negative correlations. Typically in environmental laboratory work, the analysis is looking for a direct or positive correlation. The closer the correlation coefficient is to 1.00, the less likely the responses are due to chance and more probable that the responses are due to a true change in the concentration of the standards. The 20th edition of Standard Methods in section 1020B, 4020A, and SW 846-6020B discuss the minimum acceptance criteria that should be used for the correlation coefficient when one is not specified in the method. While the criteria focuses mainly on the linear regression acceptance criteria for the correlation coefficient, you will notice that the second bullet point does mention that nonlinear regressions should also have a correlation coefficient greater than or equal to 0.995. It is important to note that the relationship measured by the correlation coefficient, or R, is not always meaningful. In other words, a 0.995 or better does not mean that the calibration curve is acceptable. In order for the correlation coefficient to mean anything, the relationship between the two variables should make sense and should be related. An example of non-rational correlation is the one between the rise in teachers' salaries and the consumption of hard liquor in the U.S., which resulted in a correlation coefficient of 0.98. In addition, the correlation coefficient must be made up of a large enough sample size to minimize the causes of variation. Along with this would be that a correlation coefficient would not be useful when using only 2 standards for a linear or 3 standards for a quadratic. In these cases, the correlation coefficient would be equal to 1.00. Occasionally, the method specifies a specific coefficient of determination rather than a correlation coefficient. An explanation of the coefficient of determination states that in a correlation analysis, R-square, occasionally called the correlation index, may be calculated most simply by squaring the correlation coefficient, R. It may be described as the amount of variability in one of the variables accounted for by correlating that variable with a second variable. In addition, as in regression analysis, R-square may be considered to be a measure of the strength of the straight line relationship. Criteria for the coefficient of determination can be found in some methods. SW846-8000C lists the criteria for the coefficient of determination, or R squared, as greater than or equal to 0.99. The last items we would like to address are some general criteria for all calibration models. These general criteria are used in the determination of an acceptable calibration curve. Midpoints of a calibration curve cannot be dropped just to meet the method criteria or the internal laboratory required criteria. Also, the calibration point or points can be reanalyzed if the point or points appear to be an outlier for part or all of the analyte list, but the original analysis of that calibration point must be discarded for all the analytes. Analysis of additional standards, for example, analyzing 10 standard concentrations if the method requires 5, and then discarding several standards just to get a better correlation coefficient value is prohibited. However, narrowing of the calibration curve on either end is allowed. For example, discarding the highest calibration standard. If the calibration range is shortened by dropping the highest or lowest point, analytical measurements must be in the shortened range.